The southwestern United States is a classic area for understanding continental extensional tectonics. It's a region known as the Basin and Range province. In this presentation, we'll be looking at the evidence for low-angle normal faults, so-called detachment surfaces, and we'll be exploring the isostatic consequences of high-displacement normal fault systems. We'll go on to look at a model proposed by Wernicke based on this region, and we'll ask the question whether this model can be applied to continental breakup. So the hills in the back are the Catalina Range in Arizona. They're a so-called metamorphic core complex, a region of elevated metamorphic rocks, in this case sheared granites and gneisses, and they're enveloped by a fault surface. Let's have a look at John Spencer's block diagram drawn in the early 1980s through this region, showing how the Catalina Range, the core complex, relates to the adjacent sedimentary basins that are bounded by normal faults. You can see that the basement that's been uplifted, the sheared granites, are enveloped by a shear zone that wraps over the range. And here it is on the cross-section drawn by Spencer and Reynolds in the mid-1980s. And the Catalina Range lies beneath one of these detachment surfaces. Here it is in outcrop with the sheared granites showing that streaked out fabric, and if we look in detail at these rocks we can see the minerals streaked out into this myelinitic fabric. So the evolution of this cross-section was cartooned up by Spencer and Reynolds, and here it goes. So they envisaged the faults as being listric in form, quite steep in the brittle upper crust, and then becoming low angle in the ductile deeper crust. As the section develops, and the Catalina Range is bulged and folded up as a consequence of movement on these fault surfaces. So for Spencer and Reynolds, we have low angle faults that form from the outset. A slightly different view was taken by Roger Buck in his model here from the later part of the 1980s. So he explored the isostatic consequences of movement on a normal fault. So he has a steep normal fault here that moves, but as a consequence it unloads the footwall because we've taken rocks off the top. The isostatic response of unloading is to create uplift, so the fault is arched, and a new fault is developed in response because the old one has been deformed. So the original normal fault is rotated to a lower dip, and a new fault forms in the hanging wall, so we're generating a splaying fault, and the old fault is rotated to a lower angle. Buck developed a quantitative model looking at the isostatic response of these processes, assuming an effective elastic thickness for the lithosphere. And what he shows here is the evolution of a fault system as it slips and unloads the footwall. Throughout this model, the active part of the fault is dipping steeply at 60 degrees. So that's after 15 kilometres extension. That's after 30, and we can see that the footwall has become pulled out from under the fault, and the old part of the fault is achieving a low angle orientation. And after 60 kilometres, we've got this geometry, so we brought up deep rocks to create a domal structure. So the exhumed footwall to these faults is what constitutes a metamorphic core complex. So the final geometry we see, where the fault has this low angle or indeed domal shape, doesn't reflect its geometry when it was moving, but rather shows the fault deforming as the footwall is unloaded. It's only the steep segment, according to Buck, that is moving at any given time. We have deep rocks exposed in the footwall to that detachment, and so-called rider blocks, these little fault segments decorating the fault surface. We can step back and look at the Basin and Range province on this NASA satellite image, and we can identify the fault systems in here and their basins by the stripy texture in the image. So we can see the stretching direction in Nevada, east-west, and down in Arizona where we were looking down there, more northeast-southwest, as the basins and this part of the crust is stretched apart. So this region has inspired a model for continental extension, generally referred to as the Wernicke Model after its proponent, Wernicke, developed in the mid-1980s, and it shows a normal fault inclined through the lithosphere like this. Normal fault is relatively gently inclined, a so-called detachment fault, and it cuts the entire lithosphere. Subsequently, Wernicke's model has been applied in many places. Gordon Lister and co-workers developed it to explain rifting associated with continental breakup. The hanging wall block moves away from the footwall. In this terminology, the hanging wall is called the upper plate. The footwall is called the lower plate. And in the model, once we get to breakup, these two hanging wall and footwall blocks move apart. As a consequence, the final pair of continental margins are asymmetric. They're asymmetric in structure, and consequently the stratigraphy of the rocks associated with these basins, and because they juxtapose different lithospheric levels, the heat flow in these systems will also be different. So the Wernicke model, as developed by Lister and others, develops predictions for asymmetric continental margins. So the Basin and Range province is important for understanding continental extensional tectonics. It's where the model for asymmetric rifting, as proposed by Brian Wernicke, was developed, where low-angle normal faults constitute detachments. A consequence of large displacement normal faulting is to isostatically unload the lithosphere, which causes doming, which may be an explanation for the presence of low-angle fault trajectories. The question is, can these models be applied to continental breakup?